So I'll just continue. So yeah, this is the this is the last class of the course, and we're gonna do like a course overview kind of thing, sort of exam review. I'm gonna mention what's on the final exam, and yeah, that's what's gonna happen. So I guess to start, there's this course survey that I guess the department recommends that you fill out. So here's the URL or the QR code to scan, and there's this link. So you can fill this out on your own time, I guess, when you rewatch the video and stuff. Okay. The other thing that I didn't actually write down right away on this review notes. Oh, also the review notes are all on the website as usual, so you can download them if you want to follow along. But I'm going to send out an email in a few days about the breakdown of the final exam. But it's going to be a similar structure to the midterm, so it's going to be like these multiple choice select multiple correct answer thing. There's obviously going to be more questions than on the midterm. And I guess the exam breakdown is going to be something like this. I haven't made it yet, but I think the aim will be to do something like this, which is I don't know how many questions there will be. Last year there was 40 questions, so maybe something around 40 questions. But the idea will be something to do like 40% of the content should be focused on stuff after midterm 2, which are chapters 9 to 11 in the course notes. So that's like all the stuff after midterm 2. And then 40% will be stuff from midterm 2 style content. So that'll be like chapters 6 to 8. And then there'll be like 20% of the stuff before midterm 2. So midterm 1 stuff, which is just like the math and probability stuff too. So something like this is going to be the aim for the final exam. So it is cumulative, obviously. And yeah, and I'll make a post on Canvas in the next few days. The exam is on the 18th. Maybe I should mention that. So the date is December 18. And it's the time, I think, is in the morning. Yeah, it's 8:30 a.m. It's 8:30 a.m. until 11:30 a.m. And so the exam is unlikely to take you 3 hours, but I had a choice of making it 2 or 3 hours, so I thought, why not give you the extra hour if you wanted to, if you needed the time. So you should be able to probably finish it in like 2 hours. Okay, so that's the high-level overview of what's going to happen. And I guess the advice is before, and you'll see this in the post, is like to really review the assignments and the past midterms, and go over like the content in the course notes with the examples, and you should be pretty much set, because as you've seen, the questions are quite similar. Okay, and the other thing is we'll still be hosting office hours until the exam date, so you can come to all of our office hours to ask any questions. Okay, and so the way this lecture is going to work is it's just going to be a review of a lot of content from the class, and the stuff up to chapters 9 and 11 are kind of a copy and paste from the first 2 midterm reviews, so I'll kind of go over that quickly. And in part, I put them all together in one pair of notes here so that you have it all self-contained to study, I guess. And yeah, so I'll go over that stuff sort of quickly, and then we'll get to the content that was after midterm 2, which we'll go over in, I guess, a little bit more detail in this class is the aim. Okay, so maybe let's spend like 20 to 30 minutes kind of reviewing the content up to these chapters, which should be a sort of repeat of the midterm reviews, and then we'll do the content after. So let's begin. So super kind of high level to start is like we had this math review stuff. We just defined all sorts of set notation and Cartesian products. Basically, we just set up all of our kind of math tools that we're going to use throughout the course. So I'm not going to go over like these details, but you can look over these notes or rewatch the midterm review videos in which we kind of review all this notation and so on. And yeah, so I'm actually just not going to go over this at all, but you can review these. But we talked about functions and like derivatives, and on the formula sheet, there is a bunch of like common derivative properties that you might need to use when taking derivatives of like gradients and things like this later on. Okay, and then we got into probability world, because as you've seen, many things in machine learning are viewed from like a probabilistic perspective, where data is kind of randomly sampled, and so you have to understand what it means for things to be random and what distributions are, and then how to take expected values and sample means and so on, as we've seen. So that's why we kind of covered this. And in terms of final exam content, you can expect like 1 or 2 questions kind of asking these simple things about derivatives or functions, with really no context about supervised learning kind of at the beginning. Similarly, for probability stuff, there's going to be like a couple of questions that just kind of ask you to see if you still remember what events are, what distributions are, what random variables are, and so on. And okay, here I can say like the high-level story was like you have a set of outcomes, and events are just subsets of outcomes, and you want to talk about like, oh, what's the probability that one of the outcomes in an event occurs? So an event is just some subset of your outcomes. And the way you do this is you have this function called the probability distribution function. It's going to take in an event, and it's going to tell you the probability of getting an outcome in that event. That's how you should think about it. And this random outcome, what we think of it, describing it through like a random variable, we use like a capital letter for that. It takes values from the outcome space, and then you can talk about what's the probability that your random, like outcome random variable, takes on some value, and those values should be like written as elements of the event. And so this kind of notation is equivalent in this course. Okay, and then we saw all sorts of common notation, which I won't really review. But really the kind of one of the important things is that we noticed that you should break down these like random variables into 2 types, depending on their outcome spaces, really. And that's because the way you're going to calculate probabilities is going to differ. So we're going to have these discrete random variables, and that's when your outcome space is countable, let's say. And you're going to have continuous ones when you have these uncountable outcome spaces, such as the real numbers or some intervals. And so the difference is in how you calculate the probabilities, and we'll kind of use a, for the discrete case, you can just kind of sum up the probabilities of each of the outcomes. And this procedure is just called like using a PMF. So there's this PMF function, which maps each outcome to a number between 0 and 1. And if you want the probability of some event, well, you just sum up all the outcomes. So it's like if you want the probability of getting a 1, a 2, or a 3 on a dice, you just sum up the probability of those. And if things are continuous random variables, well, then you can no longer kind of just sum up all of the outcomes. There's uncountably many, and you have issues with this kind of sum equaling 1. And so we found that we should talk about densities. And so densities kind of tell you the amount of probability you can imagine in some, let's say, area of something, and so then when we talk about the probability of some event, we just, instead of sum, we integrate. And we integrate over the density. And so that's the difference between if you're dealing with this discrete or continuous random variable. And this, of course, should say if x is continuous. Okay, good. And then there's all sorts of commonly used distributions which are on your formula sheet, and you should kind of be familiar with them because you're going to want to know if they're continuous or discrete, and if you should like what kind of PMF or PDF they have to calculate probabilities. Okay, and then kind of the same story went through for the multivariate case, where now you have a random variable, which is just like a tuple of random variables, such as like this tuple of x and y. And then you have like these joint distributions, which is just the probability of, you know, the multivariate random variable. There's a marginal distribution, which just kind of talks about the probability of a single one of these random variables. There's conditionals where you condition on them, and so on. There's like other rules like the product rule, which help you decompose these PMFs or PDFs for the joint case, and so on. And a very important property that we use quite often is when you have like a PMF or a PDF, let's say, of a joint random variable, well, it can be very complicated. However, if the random variables that the joint random variable is a kind of a representation of, if they're independent, so if x1 to xn are independent, then there's really wonderful property that the PMF or the PDF can be written as the product of the PMF or PDFs of each random variable. And that really simplifies a lot of math quite often. Okay, and then we saw that functions of random variables are still random variables. This happens a lot in the course because we have these predictors that take in random features. So the predictors are random variables. There's the loss functions that take in predictors and labels. Those are random. And then we take sample means of the loss to calculate like the empirical risk, as we saw. And so, yeah, so like the sample mean, which is the sum of random variables divided by n, is itself a function of random variables, so it's a random variable. Then we talked about expected values, which is just like the value you would expect to see kind of on average. It's not the value you would see most often, it's like the average value you'd see. So if you roll a dice, the expected value is 3.5, which is not a value you'd ever observe, but it is the average value of all the outcomes. And you can do the same thing for like functions of random variables, as long as those functions map to real numbers, because you have to take kind of this weighted sum and so on. And yeah, and then there was another quantity called the variance. And the variance was like kind of the deviation from the average value. So the deviation of a random variable from its expected value. And for some reason, we choose to square this deviation, and we call that the variance. Okay. Then we moved on to the actual machine learning problem, which is supervised learning. Here we have data sets, which are very big joint random variables. And the important thing was that each one of these data points, which are like feature label pairs, are independent. And that kind of helps us with all sorts of properties. And they all come from the same distribution, which also helps with a lot of like properties when we write out these probabilities. And then there was a bunch of like different quantities we talked about. So there was a learner, which took in some data set, and it produced a model or a predictor. The predictor was just a function from features to labels. And then the way we kind of quantified how well we're doing is through a loss function. So in particular, a predicted label compared to like the true label can have some error or loss. That's a real number. And then we said, okay, well, you know, we don't really know how much, well, like there's a lot of, you know, features we can care about, and each one of those features will map to some like label, and it's like, okay, how do we weight, you know, these different features and labels? Well, then we said, okay, maybe the correct weighting in terms of quantifying how we're doing as one single number is to weight it by the kind of probability of seeing each one of these features and labels, and this was the idea of the expected loss or the risk. So we also called this the risk. And you should think of this as kind of like a weighted sum of your predictions compared to the true predictions, weighted by the probability of seeing each one of these features and labels based on like the actual, like the distribution. And the important thing was that the distribution here you're comparing with, this weighted sum here, is the same one generating the data. And kind of the whole difficulty of supervised learning here is that we only observe data from this distribution, but we care about, you know, minimizing this expected value, which we can't explicitly calculate. Okay. And yeah. And so we saw that, well, the data set itself is random. So if you change the data set, well, then the model your learner might output might change. And so therefore, the risk might also be different for different data sets. That makes hopefully complete sense. If you gather like 100 houses in Edmonton, each time you gather 100 houses, they might be very different. And so, you know, the model you end up outputting based on data can also differ. So we said the real objective is going to be to kind of do well on average over all data sets. So that's why there's this outside expected value. Okay, then we talked about how you can break up these supervised learning problems into two cases depending on the labels. And it turns out this is a useful way to break down the problems because there's various differences in what happens for the objective, and it will change kind of the algorithms you want to use. And so regression is when the labels are continuous, and classification is when the labels have no sense of order, so something like cat, dog, or bird. Okay. And then the learner that we really studied throughout the course and is arguably kind of used throughout machine learning is this ERM learner, which just says, well, you know, we have data, so let's estimate the true risk using the empirical risk with data. And then if this is a good estimate, why don't we just pick the function in our function class that makes this the smallest? And if we all agreed that this risk is truly a quantity that quantifies how good we're doing, well, then you should hope that this procedure makes sense and does well as well. Because you're minimizing a number that you believe describes how well you're doing. That was ERM. Right. And then we talked about how to estimate this. Like, all we really kind of found was that, you know, the sample mean is a good way maybe to estimate the expected value of something, and that if you have more and more data, the variance, so how tightly your estimate is going to be to the mean, will kind of get better and better. So the variance will decrease as n increases. So this should make complete intuitive sense. As you increase the data, well, then your sample mean estimate is kind of more tightly concentrated around the true mean. Okay, so that was how we addressed this estimation part of the ERM. And then, like, a large kind of part of the course and really of machine learning is how to address the optimization part and how to do this efficiently and so on. And that led us into this whole topic of optimization. And you can think of optimization as either minimizing or maximizing a function. And since there's this wonderful relationship that the minimizer of a function, and this you will definitely need to kind of know for the exam, I think it's also on your formula sheet maybe, that the minimizer of a function is the same thing as the maximizer of the negative of that function. And so we might as well just talk about minimization problems, because we could always take the negation of the function and do maximization. Okay, and so if you want to do optimization, roughly speaking, in like the discrete case, you just, and discrete meaning that the input, the domain, is discrete over the optimization variable. Well, then, kind of without any extra structure and so on, the best you can do is just compare all the values. So input them into your function and pick the smallest one. But this can be very inefficient. And so it would be really nice if we are actually in this continuous case where the domain is continuous, and we can take derivatives and kind of improve the computational efficiency of optimization. So for this reason, we always kind of want our domains to be these like real numbers or multi-dimensional reals. Okay, and so that's what we studied in the course, because that's what we like end up doing for all our problems, is making kind of the optimization variable continuous. And we saw that if it's a continuous and also convex, well, then we're in good shape, because if that is the case, well, then assuming our domain is just the entire real numbers, well, then we could just take the derivative and set it to 0, and we get the minimizer. And if we had some like boundaries on our domain, well, then we should also check the edges. Okay, and convexity, for the purpose of our course, is when the second derivative is greater than 0, or greater than equal to 0. And that just means your function kind of looks like a bowl-shaped thing. And so if you take derivatives, they will, the point at which the derivative is 0 is at the minimum here. Okay, and then we saw how to handle this in the multidimensional case, which was essentially the same story. The only complication was checking if convexity holds. And what we said is that in this course, for multidimensional case, I'll just tell you if things are convex or not, because the procedure to check requires calculating like this kind of matrix of second derivatives, of second partial derivatives, and it's kind of complicated and maybe kind of defeats the purpose of understanding the high-level story of things. So yeah, multidimensional optimization, the way this works is you have a function. Now you're optimizing over a multidimensional domain. So this W could be something like RD, D-dimensional real numbers. And if you want to find the closed form solution, well, you just take the partial derivative in each dimension and set it to 0. And then you will find the corresponding minimizer. And yeah, so that's the procedure to do that. And so then we studied how does this look in supervised learning, and in supervised learning we were like, okay, well, yeah, and specifically we worked on the regression setting for a while, and there we had a domain which was real d-dimensional real numbers, labels. There's this function class, and maybe I'm just gonna go a little bit quicker so that we can get to the new content. But the idea is that, like, you set up your problem, you have this data set over feature label pairs, you have your empirical risk, and then you see that, well, the ERM problem just wants to find the minimum function in the function class that minimizes this empirical risk. And if we try to map that to optimization world that we saw, well, we don't really know how to minimize over functions, so the idea was to parameterize the function class. And so that means represent each function in the function class by a parameter. And we call this a weight vector. And one choice of parameterization is to pick linear functions. And so after you do this minimization ends up being just minimizing over weight vectors over the empirical risk. And then we know how to do things like, for instance, find the closed form solution. And if we do that, we find that the closed form solution is just this like A inverse B kind of equation, which I'm not going to go over the details, but we saw in class how to derive this. Essentially taking the partial derivatives and sending them all to 0. And that gives us the first learner we had in this class, which was this kind of closed form linear regression learner. It just calculates this A matrix, calculates the B vector, calculates an estimate of the weight vector by this equation we saw, and then it outputs the predictor, which is just this linear function, because that's the function class we chose. And visually, you should think of it like this, which is if you have some data set and you have a one-dimensional feature, well, then what happens is that we find the line, because we're working with lines in our function class, well, linear functions, and that's just lines in one-dimensional features. We find the line that best fits the data in the sense that the square distance between each of these data points, if you take that weight, like the average squared distance, that is minimized over all the data points. Then we saw that, oh, well, sometimes there's no closed form solutions, and getting so then we can't just set the derivatives to 0, so we should do something called gradient descent. And the rough idea, okay, we went through this derivation story, but the rough idea is when we get to first order gradient descent, all you do is calculate the gradient, which tells you visually, it tells you the rate of change, the steepest kind of rate of change of your function, and it points in the increasing direction, so you want to go in the negative to get to the minimum. So you take these negative gradient steps. So there's a minus gradient, which is just the derivative in one dimension, and then the step size is how big of a step you take. Okay, and in the multivariate case, yes, this step was just you had these gradients which tell you the direction of maximum increase of your function, so you take its negative to go to the minimum. And there was various procedures to select step sizes. All of them had like similar ideas, which is they're trying to somehow find some way of like changing the step size such that maybe as you get closer to the minimum thing, you don't take as big steps, or you like check the size of gradients as you get closer to the minimum and things like this. And so on the formula sheet, I don't think these are there. But on the exam, if you get asked a question about these kind of things, these will be told to you, like what the definitions of them are. So for most things, you'll be told the definition of what like these terms mean, like normalized gradient and so on, in the exam question, if it's not on the formula sheet. Okay, and then we got into the first algorithm for gradient descent, like the gradient descent algorithm, and that was just, well, your learner takes in a data set. Now it has these things called hyperparameters, such as the step size and the number of epochs. And batch gradient descent just loops over 1 till the number of epochs. This is like your choice of how long you're going to run gradient descent for. You just calculate the gradient and then take a step size in that direction. You do that t times, and then you finally output your linear function. The more steps you take with a good step size choice, the closer you get to the minimum. And visually, it should be thought of as if you had a data set, you start at the very beginning with a random guess of what the weights should be, so you have some weird linear function. And then as the gradient steps proceed, you get a function that closer and closer fits the data until eventually, if your step size was chosen appropriately and the number of steps was very large, you will get closer and closer to this closed form solution. Okay. And then we briefly talked about computation, which is the reason to use gradient descent or batch gradient descent even over the closed form solution, is that you don't have to take an inverse. And if you don't have to take this inverse, you don't suffer this kind of d cubed and nd squared computation. And so in particular, if the number of epochs is less than the dimension of your features, well, then the computation of batch gradient descent is going to be less, in the sense that if you bound t by d, then you get this big O of nd squared as the number of computational steps of batch gradient descent, which is smaller than the closed form solution. So that's kind of the computational benefit of batch gradient descent. And it can go that's all I'll say. Then we saw that there's maybe this idea that, if our data set is really big, then these batch sizes can be massive and it'll take forever to take a single gradient step. So maybe we should break up our data set into chunks called batches, and then maybe we should take gradient steps more frequently. And the trade-off there is that the number of samples used for each gradient step is smaller, so it's not as good of an estimate of the actual gradient, but you can take steps more frequently. Okay, that's all you should know. So you end up with this new empirical risk based on a mini batch M. So it's a smaller sample mean. But the advantage is that in the algorithm, you have this inner loop that now can take M times more steps. And usually the trade-off of poorer estimates of the gradient, but more steps is worth it. And something in between of the two extremes is kind of the best choice usually. So there's two extremes, which is if you set the batch size to n, then you take one step. But if you set the batch size to 1, you take n steps, which is you take a step for each data point. This is sometimes called stochastic gradient descent. And something in the middle is usually the best choice, empirically. Okay, and then we said, maybe we shouldn't always just consider lines, so let's consider more complicated functions. And the way to do that was just to map your original features to polynomial features. At least that was the idea we started with. And so that was, you had this polynomial feature map, which takes in your original feature vector and maps it to some new space, where that new space was of dimension p bar, and p bar had this form, which was just include all of the polynomial features up to degree p bar. Or sorry, up to degree p. And the story that you should remember here is that the function class based on these polynomial features p, right? The only difference is that now you use this feature map inside your function class. This function class becomes kind of richer and more expressive as p gets larger. So there's this relationship that the linear functions are a subset of polynomials up to degree 2, which is constantly a subset of polynomials of degree p, and so on. And that means that if you minimize exactly the empirical risk for each one of these, you have more functions to pick from, so your minimum can only be better. And so the relationship's the other way, which is the empirical risk is largest for the linear functions, and it only gets smaller until it gets like this technically should, this technically shouldn't be 0. So it'll get smaller and smaller, and eventually you'll be able to fit all of your data points if there's not multiple labels per x. But in the case where there's multiple kind of labels, like let's say in regression, where there might be multiple prices for the same number of rooms of a house, well, then you can never quite fit it perfectly because you have to kind of pick some value even though there's multiple data points here. Okay, so you kind of get to the smallest possible value, which might not be 0 sometimes. And the idea is that visually, it's like you get this kind of overfitting behavior. You fit the data points perfectly if you have a high polynomial degree. Okay, and then we saw that, is this really what we wanted? Does it really achieve our final objective, which is doing well on new data points or minimizing the true risk? And we saw the answer was a little bit complicated, and it depended on some things. Okay, so we return to what is our real objective, and that objective is to minimize the true risk, not the empirical risk. Here we're minimizing the empirical risk. These are empirical risks. We want to know the true risk of our predictor. That's what our learner outputs, this predictor, from this set of predictors. And we want to know how well does that do, kind of like on average over different data sets. Okay. And the learner we study is this empirical risk minimizer. And at a high level, we kind of saw that, like, when should we expect ERM to do well? And that's like kind of maybe two things, which is that if the function class you chose in ERM actually has a function that can make the true risk small, right? So this is kind of like going to be what's called the approximation error, we'll see. If you have some function that makes the true risk small, well, then you can expect to do well. But also, if you're minimizing over the empirical risk, not the true risk. And so when can you expect this like minimization to be a good idea? Well, when the empirical risk is a good estimate. And unfortunately, what we'll find is that the function class kind of has a tension between these two things, which is that obviously the bigger your function class, the better the chance that there's a function that makes the true risk small. However, if you make your function class very large, then unfortunately, your empirical risk is no longer going to be a great estimate of the true risk. And so there's a delicate balance between these two. Is really going to be your takeaway of what's coming up in the next like 10 pages. So you should remember that. So here's a little more detail, which is you have this learner, it outputs a predictor that changes with data. And so since it's going to depend on data, the choice of predictor, unfortunately, the sample mean estimate is no longer kind of it's not a sample mean over independent random variables. So in particular, each one of these losses, although these xi, yi's are independent, unfortunately, the predictor is chosen based on data, and so it depends on all of the other data points. This data set that it depends on all the other data points. So you no longer have like this independent set of random variables that you're taking a sample mean over. And so we found in general this difference between the true risk of our predictor and the empirical risk, which you could think of as just like the sample mean based on dependent random variables, is no longer going to be zero in expectation, but it's going to change as a function of things. So it's like if your function class gets more complex, unfortunately, this difference increases. And you should think of that as like this sample mean estimate of the empirical risk is becoming more and more biased. It's having more and more dependence between things. So that's unfortunate. And so, yeah, so that's what happens there. But luckily, you can kind of like address this by increasing your data set size. Okay. And so we broke up this like error at our kind of objective, which is how well is our predictors true risk? What is this? This is the final objective. How well are we doing on new data? You can break it up into 3 error terms. This was how good of a kind of like this is called the estimation error. And this is like how close is our predictor that we output, like the learner outputs, to the best in class or the best in the function class. And then there was this error of what's the best in the function class relative to the best possible. And then there was just like, what is the best you can do in this problem if you had no restrictions on the function class and you were using no data, like you just knew the true distribution and everything. And that's called the irreducible error. And the takeaway here is the following kind of insights, which is the irreducible error is due to the inherent noise in the labels. So even if you knew everything about your problem, the best you can do at predicting new data is still going to have some error, which is this irreducible error. And the only way to really decrease this is if you gather like more informative or better features. And usually this is not possible, because you should think of this as like you've already been given a data set, and so that's why it's called the irreducible error. And then there's the approximation error. This is due to, well, what kind of function class did you pick? Is it able to represent the best function possible? And that's called the Bayes optimal predictor. And so if you pick bigger and bigger function classes, this approximation error goes down. But there's this tension with the estimation error, which is unfortunately, since your data set is random, if you increase the size of the function class, you can overfit the data. And so unfortunately, the estimation error increases as you increase f. So there's tension. And the other thing we saw is that it's just always a good idea in terms of getting, for your final error, to increase the data set size if you can. And then there was this detailed plot, which I'm not going to go into all the details, but I put it here so that you can, I guess, review it offline. But the main idea is that if you plot your function class on the x-axis, so this is like the degree of the polynomials you pick, so your function class gets more and more complex to the right, what you see is the trade-off we described above, which is on the left, when your function class is not very complex, well, your approximation error will probably be large. So this is the best possible error, and green is the error you get based on the best function in your function class. It's very large because your function class is small. But this means that you can't really overfit, you can't really fit to the data very well, and so your estimation error is going to be low. That's this. And it's called underfitting. You can't fit the data well. And then there's overfitting, which is you fit the data super well because your function class is very expressive. And so that means that the best function in your function class is very close to the best possible function. F star is close to F Bayes. But unfortunately, what that means is that if you were to gather a new data set, your predictor would probably be very, very different. And so what that means is it's unlikely that this predictor that fits the data super well is actually going to predict new data points well. And so it's the idea of overfitting. And so what you want to pick is something quite like somewhere in the middle. But unfortunately, you don't have access to this true expected value because you can't just take an average overall possible data sets. And so you have to kind of estimate this. And the way to do that is to break up your data into a train and test split. And so you really just take your data set, break it up into a training set and a test set. You train on the training set, and that's everything, all this optimization stuff we've been doing. And then to get a estimate of how your predictor is doing, you use the test set. And the reason for this is now the empirical risk on the test set is no more dependence between the predictor and the data points. And so this test error, this empirical test, the empirical risk on the test set is actually quite a good estimate of the true risk. And so this is the thing you want to plot. And then if you plot this, your choice of predictor should be somewhere that has the minimum test error or test loss. Okay. And so this is a very important plot, which you almost certainly see on the exam a couple times. And what you should remember is that even though your training error goes down, that does not mean that you're going to do well on new data all the time. What you really want is the plot of how you're going to do on new data. And that would be you gather new test data, or you split your data set into this test set, and then you see how you do there. And so your choice of predictor should be based on this kind of unbiased test set. Okay, and you should understand that like on the left side, there's this underfitting. On the right side, you're overfitting to the data. And if you were like shown a picture of data and a predictor, well, here you would have like, these data points, and you have a predictor that like really fits the data because this has zero basically empirical risk. And underfitting is like, oh, you have these data points, but you have only maybe lines and you can't fit the data very well. Okay, these are the type of things you should know. And then we saw that you can also think about this bias variance trade-off as another way to talk about things. And There we saw that if you use the squared loss, then you have this decomposition. And so it's very specific to the squared loss. If you use the 0-1 loss, this becomes actually an inequality. And you should really roughly think about it as like this. Well, in the case without regularization, we saw that the variance is equal to the estimation error, the bias is equal to the approximation error. And you can just think about it like this, which is the expected predictor, so the predictor you get on average over data sets, how the bias tells you how close is that to the best possible. Well, the variance just tells you if you change the data sets, how much does your predictor vary relative to its expected predictor. Okay, and the behavior is the same. Bias goes down if function class goes up. Why is that the case? Well, function class is more representative of, has more functions. What that means is that your expected predictor has a chance of being closer to the best possible. Variance, however, increases with function class size because there's more functions that can change. You have more choice of functions to pick between, so they can vary more if the data set changes. And then we introduced this idea of regularization as like a kind of a smooth way to trade off between the complexity of a function class. So the idea is pick a very complex function class, so pick a polynomial degree that's very large, and then just change this regularization parameter, which is going to tell you like how much do you want to penalize complex predictors. So what you do is you actually change your objective from the empirical risk to the regularized empirical risk or the regularized estimated loss. You just add this regularization term that penalizes weights that are very large. And there's this observation that large weights cause for more complex functions. Or another way to think about it is that if you penalize weights more, your function class is kind of restricted to functions with small weights. And if you allow the weights to be bigger, well, that just makes the function class bigger. So there's this regularization parameter that penalizes weights. And that gives you the similar behavior, which is if you plot the regularization parameter, now the idea is actually, the plot goes in the other direction. So here this is large lambda, and here it's small lambda. So large lambda means you penalize weights more, which means your functions are less complex. We call this high bias. High bias means it's like there's a big difference between the expected predictor and the best possible. Low variance because you're not really allowed to pick many functions. You get penalized for changing the weights a lot. And overfitting is the kind of the other side. Low bias, high variance case. Okay, very similar plot to what we saw before. And the procedure for solving for a predictor with this empirical regularized risk is the same as before, except now your objective has changed. You just have this regularization parameter, and we went through how to calculate the gradient of this. So you just, since it's a sum, it's very nice. You just calculate the partial derivative of this, and then you calculate the partial derivative of this, and then add them together. You get your gradient, and then you do gradient descent. Nice. And so then at the in the course notes in section 7.6, there's this page on a summary of the errors. So maybe this is one of the important places to look for some of these takeaways. And so this is talking about how does changing n and changing the function class or the regularization affect these different error terms. And so we can just briefly look at this. Let's talk about kind of the estimation and approximation error. Well, let's talk about all three. So the observation is that increasing the size of the data set is just always a good idea if you can do it. It doesn't affect the function class, but it can increase basically the quality of your estimates. And that's the idea here of this column. This column here, the function class or lambda scaling, has the effects we saw before, which is there's a trade-off, which is estimation error versus approximation error. Well, estimation error increases because function class is more complex, but approximation error decreases because you can pick a function closer to f base until ultimately it gets your function class is so representative that f base is inside of it, and once you reach that point that f base is in your function class, well then at that point there's no value of making your function class any richer because you can already represent it. So your approximation error will only decrease up to that point, and that's kind of an important thing to know. Similar to the bias, your bias will only decrease until you have a function that's in the, that f base is in the function class. Okay, and then finally the effect. So this was the effect of the function class with the regularization being 0. And then if you talk about changing the regularization, what you'll find is a similar behavior for variance and bias. Variance goes up if you decrease lambda, and it goes, or so that then the bias decreases if you decrease lambda. You allow more complex functions. And the effects on the approximation and estimation error are like less kind of clear. Well, at least the approximation error doesn't change because you're not changing your function class. So now let's get into maybe what the second half of stuff was, which is this maximum likelihood and map and classification stuff. So I very maybe quickly go over Emily and map, and then we get into classification. So Emily was the story that, oh, you want to calculate the Bayes optimal predictor. You can just explicitly check what that formula is when you pick a loss. And if you pick the squared loss and you're in regression, you find out it's just this conditional expectation. And then you look at it and you're like, oh, I just need to know this conditional PMF or PDF here, and I'll be done. So Emily is just a procedure to calculate this, like a, let's say a PMF or a PDF. And the idea is just, you have data, you write out this thing called a likelihood, which is the probability of that data under some distribution, and you parameterize the distribution, right? So like the data is coming from some distribution, P of Z. You don't know what it is, and so you'd like to estimate it. So what you say is, well, I'm going to make some guess about what P of Z is, and I'm going to represent all those functions based on some parameter W. So you write that out, and then you have this likelihood function. And what you find out is, since the data is independent, you can write it out as a product. And so for that reason, the procedure is, I'm going to find the parameter that makes this likelihood the largest. So it makes my data the most probable given that parameter. And so then you want to solve this problem. And this is just like some tricks to make the maximization easier. You take a negative so that you're minimizing. You apply the log because this is going to be a log of a product of things. So like down here. And then the log of a product becomes a sum of logs. And then taking derivatives of a sum of things is a lot easier than the product. And the way this works for the machine learning case is the thing you wanted to estimate, if you remember, is the conditional PDF of y given x. And so to estimate that, you have to make some assumption on what is the distribution P of y given x. Well, one choice is that it's normally distributed. So for each x, there is some distribution, normal distribution, generating the y's. So that should look like this. So for each x, there's some distribution generating y's. It has this form. And you assume that the mean has this linear relationship with x. So if you change w, then you get a different relationship of the mean. So that would mean like you get a different line for the means. Okay. And so you do this MLE procedure that we've seen many times, and it turns out that you end up with minimizing a quantity like this in this special case, which looks exactly like linear regression. And so we found out that the MLE estimate of the parameters of this normal distribution is equivalent to the estimate of the weights for our linear function class in linear regression. So there's this nice view that doing linear regression is the same as finding the set of weights that describe the expected value of a normal distribution generating your labels. Okay. And the reason we cared about this is because the interpretation is going to be useful for classification. There was another procedure called map, which instead of maximizing the likelihood, it instead rewrites, instead of writing this likelihood, which is the probability of the data given a parameter, it says, what's the probability of a parameter given the data? And the way to interpret this is that you can rewrite it using Bayes' rule. And if you do that, which we've seen many times, you end up with something that is basically the same as maximizing the likelihood times a prior. And so map is thought of as maximizing the posterior, which is just the likelihood times the prior. And you should think of this, the difference between MLE and map is that now you have some weighting on the prior. So you have some prior knowledge on which parameters are kind of like more likely or less likely, and you weight your likelihood by that. And then you do the same idea, which is you take the negative log and continue the procedure and minimize. And the main takeaway was that if the data set is large, then map estimate is approximately MLE. The prior gets washed out and it doesn't matter. And if you work out any of these problems, you find this kind of behavior. And you can imagine working this out on the exam and being asked, like, if n was large, then would you expect map to be close to MLE or not close, and something like this. And the other observation is that if the variance of the prior is large, so you don't really know, you don't have much like prior knowledge on what the parameter should be, well then, once again, map estimate is close to MLE. But if you have strong prior knowledge on what the parameter should be, that means the variance of your parameter is small. And then your map estimate will actually be very, very close to the expected value of your parameter, which makes sense. If you have a strong prior, then your estimate should be actually very close to just that prior. So data won't do much. Okay. And then you do the same procedure for the supervised learning setting. You just have to assume some sort of prior on the weights. If you choose a normal distribution for the prior of the weights for some reason, which is saying like with expected value 0, so if for some reason you think the weight should be centered around 0, and then you pick a variance of 1 over lambda for a reason that becomes clear in the future, and you go through this procedure, you find that actually the thing you're minimizing looks very similar to the empirical regularized risk. And so one way of viewing the regularizer is it's a penalization based on how strongly you believe in a prior. The larger lambda is, the smaller the variance of your prior, and therefore you have a stronger prior on the fact that the weights should be closer to 0, which means you penalize weights that are larger than 0. And that gives rise to another idea, which is like, let's change the prior to something like a Laplace, see what we get. Well, what you get is a different regularization kind of penalization factor. And this is called lasso regression. And you can make other changes to this. So stuff like this. You can imagine maybe going through this kind of derivation on your final exam, but for the one-dimensional case where you can actually take derivatives and so on. Yeah. So you should know that. Okay, and then we get to the new stuff, which was classification and neural networks and so on. And the way this worked was your labels are now unordered. Usually there's like finite set of things. And there we really want to minimize the 0-1 loss because there's no reason to kind of weight one label more than the other. And yeah, so this is what you care about. But unfortunately, the 0-1 loss is not continuous, so we're going to have trouble optimizing. And so we're like, okay, what do? We can, at this point, just make some, we can pick some different loss here and try to just, optimize over that. But it's kind of confusing what you should pick for this loss. And so we're going to do it through a different, more principled maybe way, instead of just making some rough guess at what this should be. And that way is rewriting, writing out what f base is and seeing what it's going to be for the 0-1 loss case. So we did this for the squared loss. We saw it's this expected value of y given x. For the 0-1 loss case, it turns out to be the, you just pick the class or the label with the largest conditional probability. That should make complete sense. If you're given a new feature, you calculate the probability of each label. You just pick the one with the largest probability. And that's the best you can do. And the key observation is that what you want now is to calculate this conditional PMF. And luckily, we have MLE or map to do this for us. So if we go through MLE, we set up the problem. The most important thing in MLE is to pick your assumption on what is the distribution over your random variables. In the binary classification case, it's very simple. There's only one choice of distribution, which is the Bernoulli. It's the probability of getting 1 is something, and the probability of getting 0 is 1 minus that. However, the Bernoulli parameter, which gives you the probability of 1, should depend on x, which means if you change the feature, the probability of getting label 1 should probably, change. And so the question is, what do you pick as a function here? And the natural choice is you should pick some function that depends on x and is between 0 and 1. And one choice for this is what is called the sigmoid or logistic function. So this function is always between 0 and 1. And it has this kind of behavior, like it looks like this. And we input into it this linear function, which depends on some weight parameter, w. And so, roughly, all you should think about is that now this parameter, which is what our distribution is described by, you just need this one parameter. It is a function of x, the input, like the feature. However, it's parameterized by some weight vector w star. And so all we need to do is find w star, and we have found this parameter, and we know what the PMF, the conditional PMF is. And that's really nice because now when you write out the maximum likelihood objective, you end up with an optimization problem over these weight vectors, which if you find the weight vector that's closest to w star, or you find w star, well, then you know the probability of getting a label of 1. So you write out this MLE thing, you get this objective, it's convex, it turns out. That's another reason to pick this function in particular. And then if you take there's no closed form solution, so you do gradient descent. So if you take the partial derivatives of this and group them into a gradient, you get something like this, it turns out. Something quite nice and simple. So maybe on the exam, you could imagine working this out for the one-dimensional case so that you don't have to take all these partial derivatives or something like this. Maybe having some small change in what we choose here or something like this. Because, yeah, in class, we went through this whole procedure of going from here to calculating this gradient. And so you can imagine just having a small change up on this procedure to see if you know how to work out these steps and the idea of where to go. Or you might just be asked, what is the next step you should do if there is no closed form solution, in which case you should apply gradient descent, and so on. And yeah, so you calculate the gradient. It has this very similar form we've seen before, which is prediction minus label in your data set times feature. Turns out this is actually a general property of a more larger class of losses called generalized linear models, which we don't study in this course. And the observation is what we've now found is the probability of getting a label of 1. And so the way we're going to predict things is we're just going to remember that F Bayes picks the label with the largest probability. So we replace the PMF with our estimate of it. We replace it with the MLE estimate of the probability of some label. And then we call this procedure of picking the class, the label that maximizes this estimate of the PMF, our binary predictor. And the way to maybe interpret this is that you can expand this and recall that, well, this is the probability of getting class 1. And so what is that? Well, that's just our estimate of the parameter, which is this thing based on WMLE. And you can see that, oh, well, we're going to predict label 1 if this estimate is greater than 0.5 or less than, and we're going to predict 0 if it's less than 0.5. And if you just look at the sigmoid function closely, you find that the input, when will the sigmoid be greater than 0.5? Well, that's when the input is greater than 0. So equivalently, that's the same as saying, I'm going to predict 1 if the input to my sigmoid is greater than 0. And that's a nice interpretation because this gives rise to a decision boundary. So this is an equation when it's equal to 0 of what is called a hyperplane. And you can draw that hyperplane, which is essentially just a line when it's two-dimensional. And we've seen that before. Okay. And there's this equivalent view of binary classification with MLE through logistic regression. And the idea is, well, all we were doing was estimating this PMF and then, picking the max label. Turns out that estimating this PMF can be thought of as just a regression problem, where you're trying to estimate one number, which is the probability of getting class 1. This is a continuous value, so it turns out this is equivalent to solving a regression problem. And we call this regression problem logistic regression, because we're going to solve a regression problem using a logistic function class. We're going to use sigmoids or logistic functions for the function class. And so the way it turns out that if you write out the regression problem with labels between the 0-1 interval, you pick this loss to be this cross-entropy loss, which you only know in hindsight after doing MLE that this was a good choice. And if you pick your function class to be the sigmoid, which once again, kind of only in hindsight, you realize that this was maybe a reasonable choice of the function to pick. Well, then if you just write out the ERM solution, you basically just write out what is the empirical risk, you get this quantity, and you find out this is exactly the same quantity, except for this 1/n factor, that we were optimizing over, minimizing, in MLE. And so we already know what that solution was. That solution was FMLE. And so yeah, this is the equivalent view. And then for multi-class case, the procedure was virtually the same. The only difference was on the assumption of what the conditional PMF is. And there, since there's multiple classes, you can't just use a Bernoulli, and the natural choice now is this categorical distribution. And this distribution is kind of silly. It has a name, but really it just has a parameter for the probability of each label or class. So the probability of each class is just the value of these parameters. They, of course, have to sum up to 1. And so if you estimate each one of these parameters, you now have an estimate of the probability of each class. And you can just use that to then select which class you're going to predict. Okay, and so that then we have to make a choice for a function for each of these parameters. And we just want, like intuitively want a function that, maps x's to numbers between 0 and 1. And if you sum up all these parameters, they give you a number that sums up to 1. Turns out the softmax function achieves this for us. So then you just go through the same MLE procedure, but the only thing that changes is you replace the conditional PMF not with the logistic function now, but with the softmax. Okay, and if you go through all that, you end up with some objective. Turns out it's also convex due to this choice of softmax, which is maybe another motivation for picking it. And if you then try to find the closed form solution, you find that you can't. And so you want to use gradient descent. And if you do gradient descent, the gradient is as follows. And so we didn't quite work through all the steps in class, but in the course notes, there's these steps. On the exam, you can imagine maybe asked why some of the steps go through or something like this, or what is the next step and why, or like maybe working through it in the one-dimensional case or something like this. And so, yeah, so then you just do gradient descent to find the solution to MLE. What does this WMLE parameter give us? It gives us, once you plug it into the softmax, right? So once you plug it into softmax, it gives us the probability of class Y. And if we have the probability of each class or each label, we can use that estimate, which is based on the MLE parameters, as a replacement for the true PMF. So if we return back to F Bayes, it's like, we just need to pick the class with the largest probability. Well, let's replace the true PMF with our estimate based on MLE. That estimate is just the softmax function with inputs, these MLE parameters. And that is going to be our multi-class predictor. Okay. And similar to the binary case, the multi-class case has a regression view. And the regression view is that, well, we just needed to estimate the probability of each class. If there's k classes, we have to estimate k probabilities. These are like continuous variables or values. So we just need to solve k regression problems. Sometimes this is called like multi-output regression. And we know how to do this. And that's just like Your labels are now these k-dimensional vectors. They're between 0 and 1, representing probabilities, representing these parameters, the values of each, the probabilities of each class or label. And so since our labels are now these vectors, you encode each of your data points into vectors, in particular one-hot vectors. So if you encode each data point into a one-hot vector. And then your loss ends up being this multi-class cross-entropy loss. Why do we pick this loss? Well, it's all done in hindsight, which is after you work through the MLE thing, you go back up here, you look here, you're like, this is my loss. I'm going to give it a name called the multi-class cross-entropy loss. It's also sometimes called the log loss. And then what is my function class? Well, my function class is going to be the things I use to predict these parameters. Well, what did I use? Well, I used softmax function. So that's going to be my predictor. It's going to be a softmax. This is a vector valued function. It outputs k numbers representing the probabilities. Turns out then that this whole ERM procedure, which minimizes the empirical risk, if you just plug in the multi-class cross-entropy loss and you minimize over the softmaxes, if you just map it back to the MLE setting over here, you will find that this indeed just looks the same, and you're minimizing the same function. And so you can think of this MLE procedure as the same as ERM with these particular losses and particular function classes. So that's something very kind of important to know, I guess. So the ERM solution is the same as MLE, but with the specific choice of course, loss and function. And so this will be called softmax regression. Finally, we in the course notes, there's a discussion about this. Maybe there will be one question or something on this, but you might wonder, how does logistic regression compare to softmax regression? Well, in softmax regression, when k equals 2, you have two labels. So they're the same setting. But there's this categorical distribution for softmax, or that you assumed in MLE, but for binary case, there's the Bernoulli. Turns out that if you solve for the MLE parameters, the softmax at the first index, which represents the probability of getting the first label, label 1, is the same as the sigmoid. And I guess you can see the course notes for those steps. Okay, so to finish, we just need to go over neural networks and these language models. And for neural networks, what you really just need to know is, how does a neural network, like a neural network is just a function. So that's all that's really changing. Your function class is now neural networks. So the thing that's really left to know is, how does a neural network work from input to output? So you should remember the information flow is from left to right. This is your input. This is your output. And now you can imagine all sorts of questions about, oh, if I have this many layers and this many weights, or neurons in each layer, how many weights do I have? Or can you implement, I don't know, can you represent a linear function using a neural network? How many layers do you need, and so on. So we saw all these things. And there was explicit equations for all this stuff. I'm not really going to go over to the mathematical details, but I'll just tell you the headers, what do you need to know a neural network? You just need to know how many layers does it have, right? So layers 0, 1 to B. How many layers will tell you part of what is called the architecture. The other thing you need to know is how many neurons are in each layer. So here there's 1, 2, 3, up to D to the 1 neurons, and so on. So each layer can have a different amount of neurons. That's the other piece of information you need to know. The third piece of information you need to know is, what are the activation functions used by each neuron? That was this activation function here. So once again, you need to know number of layers, number of neurons in each layer, activation function, and the value of each of these edges, which are the weights. If you know those four things, I can give you an input and you can produce the output for me. That's what you need to know. And if you don't know the weights, but you know the other three, you have a neural network architecture. And the way ERM works with neural networks is very simple. It's like we saw before, but you just change your function class to be neural networks. And in particular, you will pick an architecture beforehand, and then the only thing left to change the neural network is the weights. So this will be the set of all functions that are neural networks, with a fixed architecture, but different weights. And so what you're going to do is now in ERM, you're going to search over weights, right? The weight matrices. And so the way you search over this is you try to do ERM. So you try to minimize over the set of weights that define a neural network that minimize this thing, which is the empirical risk. Everything's the same as before. Unfortunately, like as we've seen, there's no closed form solution, as we've seen with many problems. And so you have to do gradient descent. So that's all fine and good. And doing gradient descent with neural networks is often called backpropagation, or at least calculating this gradient is called backpropagation. And we don't go over the details of that in class, but you should kind of know that that's what you would want to do. And there's this unfortunate thing, which is that like the empirical risk, unless you pick a very specific neural network and a specific loss, is usually not going to be convex. And so you will not find the global minimum. And so how to deal with that and whether that makes sense and so on is kind of a future topic, not covered in this course. Okay, and then finally for language models, what you kind of need to know is what is the type of language models we studied and what is it. So we're going to just care about language models in the sense of language models that generate text. And so what you would like is this behavior, which is that if you give an input a question or some sentence, you would like to complete that sentence correctly in some sense. Okay. And we studied specifically these autoregressive language models, which are language models that generate one token at a time and then reuse its output to get appended to its input to generate new tokens. So they generate outputs sequentially using their previous outputs and the inputs that. And so the procedure was like this, which is like you have an input, you generate one token. You then append that token to your input, and then you generate a new token, the next output. Then you append that to your input until you finally get to the very end, which is signaled by your network or your output by this end of sequence token. This means, okay, stop, I'm happy with my output. Now you can output this to the user. And so this is really how language models that you interact with now all work. They do this next token prediction, and when they finally output end of sequence, they stop outputting, and then you can, well, you actually see the generation kind of live. You see these tokens literally being output one after another, and then once it ends, that means the end of sequence token was reached. And then the only thing really to address was how to deal with these discrete tokens, right? That was really the challenge, because all you need to do is just predict the next token. Well, there's a finite number of tokens, so that looks like multi-class classification. Just need to predict which class or which label do I want to output. The only difficulty was now to deal with these like discrete objects, discrete inputs and outputs. And that's all that we really needed to do. And then we just reuse multi-class classification knowledge we already know. And so we start with like, oh, we want a model that's going to take in a sequence of tokens and then map it to a next token. And we replaced words with tokens because we saw, oh, we don't just want to output words. We want to also be able to output like punctuation, like spaces and apostrophes and things like this. We also maybe want to add this end of sequence to signal we're done, and this pad token for reasons we see a little bit later. So you have this finite vocabulary, which you should think of as you have a finite set of labels. So since it's finite, we call the number of tokens k. It could be a lot, like 50,000, for instance. Maybe there's 50,000 words, something like that. But nonetheless, it is just a finite set of labels. But as we have seen before, predicting labels is not good for optimization. So we instead will predict the probabilities of each label, as we did in multi-class classification. So that's the change. So we predict the probability of each next token. So now we have this probability model. Okay, and the probability model outputs a giant vector, which is of dimension number of tokens, each with some probability of that next token. And visually, you should think of it like this. You can use some neural network, which is going to take in some feature, which we haven't quite described how this is going to look yet. It's going to output a linear, it's going to have this like final linear layer. So its final output layer is going to be this linear layer. So the activation will be the identity. And then you put that through a softmax, which will then produce this k probability vector, or these k probabilities, which is a probability vector of k dimensions. The last thing to kind of address is how do you represent a sequence of S tokens, which is a sequence of S discrete objects, as a vector. And the key idea here is to just map each token, which is just a discrete object, into a vector. And we're going to call this dimension of d prime. And if you can do that, what you can do then is you can map each token in the sequence to a vector. So you push it through this embedding function, each token in the sequence. So you have a sequence of C tokens. You then get C embedding vectors. And then what you do is just concatenate them into one giant vector. So that's this concat and bias thing. And we're going to call that whole procedure embedding function bar, which is like the joint embedding, I think is what we call it. And so the joint embedding function will take as input some sequence S and produce a vector X in dimension R of D plus 1, where D is now the dimension of each embedding multiplied by the length of the sequence, which we call the context length. So to make this work for regular neural networks, you fix the context length to some size C, which is now you expect all your inputs to be of size C. And the way we're going to achieve this is by saying if a sequence is longer than C tokens, you take the last C tokens. However, if it's shorter, well, then you pad the start of it with this pad token. And modern language models that use transformers and not these multi-layer perceptron neural networks don't have this problem, actually, where they need to choose some fixed context length for this reason. There, it's really a computational reason. But for this course, to make this work where we have always had fixed input sizes, this is how we do it. And the intuition you should have with embeddings is they somehow encode semantic knowledge of tokens into a vector space. So like synonyms, like the word big and large, will be close in the vector space. And you can have relationships. So like the difference between the man vector to the woman vector is likely to be very similar as the difference between the king vector and the queen. And then to wrap things up, you basically create your data set so that we can run ERM. You just have a giant sequence of things, which you could think of as like a book. You break it up into inputs of size C and outputs of size 1 token. And then you have a data set from this giant sequence. You then encode each input sequence using your joint embedding. So then you end up with n vectors. And then you encode your outputs into one hot vector so that you can do this multi-class classification. That's your data set. Then you just run ERM with the function class being neural networks with a fixed architecture, where the output is just the softmax applied to the output. And the loss is still the multi-class cross entropy. And so for a new sequence, what you do is you take that new sequence, which has to be of length C, so you compress it into length C, the way we talked about. You map it through your joint embedding. You then map it through your probability model that you learned through ERM. And then you end up with this giant vector of k predictions. And you pick the argmax of those k numbers, which is the largest probability. And so that's one way to do it. And then we said in modern language models, people actually sample from these probabilities. OK, and so that, I guess, is the summary of all the content for this course and for the exam. And yeah, I guess thank you for attending the course, and good luck on the final exam.